Deep beneath the bustling streets of our modern cities, a mechanical titan is slowly eating the earth. It is a tunnel boring machine, a subterranean factory stretching the length of 2 football fields. With relentless force, it grinds through solid rock and thick clay to carve the arteries of our civilization. But occasionally, in the pitch black, this unstoppable force hits an immovable object. And when the machine cannot go forward, fragile human beings must step out in front of it. They are stepping into a void that is actively trying to crush them. They are hundreds of feet underground, often directly beneath a massive river or ocean inlet. To survive this hostile frontier, they must do something completely counterintuitive. They have to go diving. A halted tunnel boring machine, or TBM, is a multi-billion-dollar crisis. Entire urban infrastructure projects freeze when the massive spinning cutter head gets damaged or clogged. But you cannot simply open a door and walk out to fix it. The earth above is heavy, saturated with groundwater, and desperate to collapse into the tunnel. If you open the bulkhead, the pressure of a subterranean river would violently flood the machine in seconds. It is an environment as lethal and unforgiving as the vacuum of deep space. The pressure pushing against the front of the machine can be 5, 6, even 7 times higher than the atmosphere on the surface. To step into that space without being crushed by water and mud requires a mastery of physics. It requires transforming construction workers into extreme deep-sea divers. To understand this daring maneuver, we first have to picture how a TBM actually works. Imagine a colossal steel earthworm. Its face is a spinning disc studded with tungsten carbide teeth designed to chew through geology. As it chews, it swallows the excavated dirt through a specialized chamber, passing it to a conveyor belt on its back. Simultaneously, it builds a perfect concrete tube behind itself, inch by inch. The front chamber of this mechanical worm is a very delicate balancing act. It is filled with a thick, soapy mud called bentonite slurry, or highly pressurized earth. This pressurized mud pushes outward, perfectly countering the immense weight of the earth and water pushing inward. It acts as a liquid shield, keeping the tunnel face from collapsing while the machine grinds forward. But the earth is full of surprises. A nest of massive, abrasive glacial boulders, a sudden change from soft clay to solid granite. Over weeks of grinding, the steel teeth on the cutter head become dangerously worn down. If they are not replaced, the spinning disc will overheat, warp, and destroy the entire machine. The TBM must stop, and humans must enter the pressurized chamber to change its teeth. This is where the procedure known as a hyperbaric intervention begins. First, the engineers must create a bubble of breathable space right at the cutting face. They carefully pump compressed air into the front chamber, pushing the mud and water down to the lower half. This forms a pressurized air pocket at the top of the machine, holding back the immense weight of the earth. The pressure in this bubble exactly matches the crushing geological pressure outside. Next, a specialized crew of hyperbaric workers prepares for the dive. They are not donning wetsuits or scuba tanks for a typical underwater swim. Instead, they enter a small steel airlock located just behind the massive cutter head. The heavy steel door clangs shut, sealing them inside a tiny echoing tube. Then, the great compression begins. Valves hiss loudly as compressed air floods into the tiny lock. The atmosphere grows thick, heavy, and sweltering hot as the pressure rapidly multiplies. The workers must constantly equalize their ears, just like descending in an airplane, but far more extreme. As the pressure increases, the nitrogen in the air begins dissolving into their blood and tissues. Their voices shift into a cartoonish squeak, an eerie side effect of the dense air changing how sound waves travel. Once the pressure in the airlock matches the crushing pressure of the bubble in the excavation chamber, the inner door finally opens. The workers crawl through a narrow hatch, entering a surreal, muddy cavern. Above them is the raw, exposed face of the earth, held back only by invisible compressed air. Below them is a dark, churning pool of thick bentonite mud. They are standing in the belly of the beast. Now comes the grueling reality of the job. This is not graceful swimming. It is back-breaking heavy labor performed in an environment that is constantly trying to kill them. They must lug massive hydraulic wrenches and replace steel-cutting discs that weigh up to 300 pounds each. And they must do this while moving through thick, sticky mud, wearing heavy protective gear. The dense, pressurized air acts like a heavy blanket, making every movement exhausting. Worse still, the high oxygen levels create a severe fire hazard. The single spark from dropping a wrench could trigger an explosive inferno inside the chamber. Tools must be made of special non-sparking alloys, and strict protocols govern every single motion. It is a delicate, high-stakes ballet performed in the dark, but the greatest danger is not the earth, or the mud, or the fire. The greatest danger is the air they are breathing. When the teeth are finally replaced and the workers retreat back into the airlock, the trap is set. Their bodies are completely saturated with dissolved nitrogen gas. If the pressure in the airlock were released suddenly, that nitrogen would instantly turn back into bubbles in their blood. This catastrophic condition is known as the bends. It causes agonizing joint pain, paralysis, and can easily be fatal. To survive, the workers cannot simply walk out of the machine and go home. They must undergo a painfully slow process of decompression. The pressure in the airlock is reduced by tiny increments, allowing their bodies to slowly exhale the trapped nitrogen. Depending on how deep they were and how long they worked, this decompression can take hours. In extreme cases, they are transferred via a pressurized shuttle to a larger habitat on the surface. There, they might spend days living inside a cramped steel cylinder, waiting for their blood to safely off-gas. They eat, sleep, and pass the time in a pressurized purgatory. All while the people in the city above go about their day, completely unaware of the astronauts living beneath their feet. Finally, the pressure gauge reaches zero. The heavy steel door swings open, and they breathe the thin, sweet air of the surface. Back down in the dark, the bubble of air is released, and the chamber floods with mud once more. The massive motors hum to life. The fresh steel teeth bite into the rock, and the subterranean factory grinds forward again. Next time you ride a subway beneath a river, or drive through a gleaming new mountain tunnel, pause for a moment. Look at the smooth, curved concrete walls rushing past your window. That modern miracle of transportation was not just built by giant machines. It was made possible by human beings willing to step into the crushing void. It is a profound testament to our engineering ingenuity. We have figured out how to temporarily hack the immense physical forces of our planet, just long enough to slip inside and perform surgery on a steel giant. But as we push deeper into the Earth, building larger tunnels under deeper oceans, we have to ask ourselves, just how much deeper can the human body dive before the Earth finally pushes back?